Okay, so compared to language in general, reading is this very new invention for our brains. It's something that we're making our brains do, even though our brains really have not evolved to read. It's a kind of a new skill that our brains have to deal with. And given that, it's perhaps not so surprising that some brains actually have a really hard time with it. And that's what we'll talk about now. So we'll talk about dyslexia, which is a developmental disorder in which reading is very difficult. So I want to ask the question, what distinguishes the brains of individuals who learn to read easily versus those who struggle? And also, what distinguishes reading brains, so literate brains, from non-reading brains? So the brains of illiterate individuals. And we're starting to have some really interesting research on that as well. Okay, so let's first define developmental dyslexia. So developmental dyslexia is a situation in which reading development lags behind other academic development. Achieved reading skill is usually limited, your reading is slow, and especially non-word reading is impaired. So when you're reading a non-word like might, it does not hook up with meaning, so that connection between orthography and meaning is absent, and so then you're fully depending on the orthography to sound connection. And developmental dyslexia is really common, so it affects about 10 to 20% of the population. Something like 4% of that population has really severe reading impairment. It's also quite a bit more common in males than in females. But most importantly, being dyslexic has nothing to do with how smart you are. So you can be dyslexic and be an amazing actor. You can be a celebrated scientist. You can be an author. You can even be a poet, or the Renaissance man of all times, or you can even be George Washington. So these are all very famous people with amazing careers. They all have dyslexia. Dyslexia has nothing to do with your talents or creativity or skill or smarts apart from reading. Okay, so how are dyslexic brains different from non-dyslexic brains? So we've learned a little bit about the organization of the ventral surface of the temporal cortex and how higher level vision works in these areas. So here what I'm showing you is the fusiform gyrus in both hemispheres, so on the right and the left. So imagine that you're looking at, say, my brain from the bottom like this. So this is right and that's left. And we know that on the right side, we have an area that's called the fusiform face area that responds more strongly to faces than to other categories. And we've also learned that on the other side, the left side, we have the visual word form area that responds more strongly to words and word-like stimuli. And both of these areas get input from earlier visual areas in the occipital cortex. So this is one system that we can ask the question about whether dyslexic brains differ from non-dyslexic brains. So let's start with that lower level of processing, so the earlier occipital regions. And so now I'm going to introduce a similar stimulus design that we to the one that we discussed before. So here we have letter strings embedded in various degrees of noise, and then we're also comparing the letter strings to just strings of symbols. And let's look at that early occipital activity that is not supposed to show any specific sensitivity to the letter string versus symbol string contrast. So here on top we have non-dyslexic control subjects. This data is from MEG, and we see, just as we would expect, that the word responses do not differ from the symbol responses, but then the kind of a purely physical manipulation of noise does matter for the signal amplitudes. And the point here is that we see a similar pattern in the dyslexic individuals. So when it comes to this activity, the visual M100 activity, we see the same effect of the stimulus manipulation in the controls and the dyslexics. So we don't think this kind of early visual perception is different in dyslexic brains. However, when we move on to the slightly later response component, the component M170, which we think originates in the visual word form area, we actually do see a difference. So here we see, again, the control and the dyslexic data. And so now here, as we would expect in the control individuals, the words now elicit a higher amplitude in this response than the symbol strings. That's the letter string sensitivity that we learned about last time. And now when we compare this response to what we see in the dyslexics, basically what we notice is that the dyslexics just have very little activity in this region to begin with, and we don't see the same difference between words and symbol strings. So little activity, no increase for words or symbols. Okay, so although the occipital cortex is not different between the two populations, the visual word form area is. What about the fusiform face area then? So far the data are compatible with the hypothesis like, oh, this like fusiform system is just impaired. But now let's see if we can, whether the impairment is general or more specific to visual words. Here's a similar kind of experiment, but now we're using not word stimuli, but faces and other objects. So we have line drawings of faces embedded again in different degrees of noise. Then we have line drawings of objects. Then we have line drawings that take the visual features from these face stimuli and just like garble them around so that you maintain the low-level features, but the holistic percept is now very different. And we also have photographs of faces and photographs of objects. And what we see is that the dyslexics and the control subjects, non-dyslexic individuals, show exactly the same pattern of responses in the activity that originates in the fusiform face area. So this is MEG data. So we get the time course and we know that this activity, just like the M170 associated with words, peaks in a similar time window. So here's a kind of busy bar graph, but the dark bars are the dyslexics and the lighter bars are the controls. And you can see that those amplitudes are going very much in sync. And just like we would expect for face sensitive activity, we see these higher amplitudes for faces than for objects. And so here again, the photographs of faces, and the general pattern is very similar. So it seems like their face activity is normal or the same as for non-dyslexic individuals. If you look at these bars carefully, you might notice that in several cases, like for these level 8 faces, so this kind of face, and for the photographs of faces, the dyslexics do show a little bit less M170 activity or fusiform face area activity than the control individuals. And that's actually a finding that has been independently confirmed in later research. So we actually know that the fusiform face area of dyslexic individuals responds a little bit less in the right hemisphere than in non-dyslexic individuals. And Stan DeHen, who has done a lot of research in this area, has a really interesting theory about that. So let's walk through that a little bit. And the crucial insight comes from research on illiterate brains, so brains that never learned to read. And it turns out that such individuals show a much more bilateral face perception system than literate brains, literate individuals. So usually we think that the fusiform face area is in the right hemisphere, but these individuals actually show a face response that is more bilateral. And so the picture is more like this. So obviously now these individuals don't have the visual word form area because they never learned to read. And so it seems like in the area that the visual word form area would typically occupy, these individuals actually process faces. They have this more bilateral face processing system. And so then what seems to happen when you start, if such an individual starts to learn to read, or when we start to learn to read as children, the need to represent word forms is introduced into the system. And those representations want to go into the left hemisphere. And we talked a little bit about how they might want to piggyback on this area that represents certain types of line junctions. And so that area starts to kind of like occupy very similar cortex to the face processing area. And so the idea that's advanced in this hypothesis is that what happens is that these word representations kind of push the face processing fully to the right hemisphere, and the visual word representations take over the left hemisphere real estate. And so that's how we end up with this asymmetry between the right and the left in the literate brain. But the illiterate brain doesn't have this asymmetry. It has a more bilateral face representation. And so the face processing of dyslexics can actually look more similar to the illiterate brains because their visual word form area hasn't fully developed. And for that reason, that area also hasn't shoved the faces fully to the right hand. So that's a relatively recent account that I think is interesting. And so to complete this picture then, for the FFA, fusiform face area, we want to see something a little bit more nuanced, something like it seems to have the same functional profile as in non-dyslexic individuals, but there's overall less activity, or at least that's what a lot of studies seem to suggest. Okay, so that tells us something about how dyslexic brains are different from non-dyslexic brains. But so then, of course, we want to know the answer to the why question. So why is the visual word form area of dyslexics underdeveloped? Why does that happen? Well, the visual word form area very much represents the connections between symbols or like graphemes, the characters that function as the form representations in the writing system, and speech sounds. And there's a very interesting data from training studies that show that if you are taught to develop novel correspondences between speech sounds and characters, like you can imagine that I would give you like a new set of characters, say from some language that you do not speak or you're not familiar with, and I'm going to tell you like, okay, this character corresponds to and so forth. We actually know that we can drive visual word form area activity very quickly via this kind of training. So it really seems to represent those correspondences. And so now, most likely, this process of developing the correspondences is what's impaired in dyslexia. And that's then what leads to the lesser development of the visual word form area, because it's like the correspondences just are not crisp in the way that they are in a non-dyslexic brain. And so now, critically, in order to be able to learn these correspondences, you have to have the ability to think about the sounds of your language, because you're trying to kind of parse them and pair them with these letters or characters. So there has to be this kind of like conscious awareness of the sound system of your of the sounds of your language, and that's something that we call phonological awareness. And an impairment in phonological awareness is by far the most consistent generalization across individuals who have dyslexia. So actually, dyslexics are a pretty heterogeneous group. There's a lot of differences between dyslexics, and for that reason, oftentimes behavioral data from different labs that study dyslexia is not consistent. But the phonological awareness generalization does seem to cut through the literature pretty consistently. Okay, so when we talk about phonological awareness, we're specifically referring to your ability to do various kinds of manipulations with the sounds of a word. So your ability to judge the number, order, and sameness or difference of the sounds in a word. Also something like your ability to replace the sounds in a word. So for example, here would be a phonological awareness task. I could ask you to change the first sound of all of the following words to cough. So then you would go like cat, kit, whore, cows. Okay? So for a non-dyslexic individual, that's pretty easy, but for a dyslexic individual, that can be really difficult. At the same time, your lower level auditory perception is unimpaired, though I should say that there has been a big debate about that, but that's more or less what's true of the population at large. Also, the phonological representations are normal. One hypothesis that you could entertain is like, okay, well, maybe there's just something, you have your lexical entries in your brain, and there's a representation of the sound sequence cat. Maybe there's just something funky about that representation that then makes it harder to connect the representation to an orthography. That's wrong. That's a wrong hypothesis, and there's a compelling evidence to show that. We also know that just simply from the fact that dyslexics don't talk funny. They talk just fine, so they're using the representations, the phonological representations of their language completely normally, including in comprehension. However, what seems to be difficult is this conscious access to sound representations. And therefore, it's hard to manipulate the sound representations consciously in these kinds of tasks. And then when you're trying to develop the correspondences to the orthographic representations. One question that's always interesting to think about is whether the rate of dyslexia depends on the language. And the reason that comes up is because the orthographic systems of languages differ, and also the transparency between the phonology and the orthography varies a lot between languages. So, for example, we can ask the question of whether dyslexia is more common for languages where the orthography to phonology correspondence is less wonky than in English. So anybody who has learned to read in English or has otherwise learned English as a second language has had to tackle with the fact that the correspondences between orthography and phonology are quite irregular. So for example, we have like identical orthographic sequences, like here the red part, and they're pronounced totally differently. So couch, touch, what sense does that make? Through, tough, what sense does that make? Similarly, we can have a totally different orthography, but still the same sound. So but, hair, they sound the same, but they're spelled differently. So that's a pain about English. However, the answer to this question seems to be no. So it is not the case that we have more dyslexia in for languages where we have these kind of crazy relationships. So that's not fundamentally what dyslexia is about. So dyslexia is just as common in, for example, Finnish. So that's my native language, doesn't have any of this insanity. In Finnish, the orthography to phonology relation is always totally one-to-one, completely predictable. But we still have roughly the same rate of dyslexia. So no matter how hard or easy the orthography to phonology mapping is, dyslexics seem to have trouble with it. We can also see this in fMRI recordings from the visual word form area. So remember, we've learned that the visual word form area does not respond to letter strings very strongly or at all in dyslexic individuals. And here we see that that cuts across languages. So this is data from normal and dyslexic individuals in the UK, so that's English speakers, Italy, and France. And the contrast between the normals and the dyslexics is the same in all of these languages, even though the transparency of the orthography to phonology mapping varies. So Italian here is the most transparent one, like straightforward relationship, then French, and then English. So in conclusion, we still don't know the answer to the really hard why question, which is why some brains come into the world dyslexic and others do not. We know that at least to some degree is genetic. So dyslexia is heritable to some degree. But the genetics are complicated, and this is an active area of research and has been an active area of research for a long time. But what we are beginning to understand quite a lot about is how reading changes your brain, and how consequently the brains of non-readers and poor readers are different from those of good readers. And so it turns out that the brain of a fluent reader actually even responds more strongly to auditory language than the brain of an illiterate. So it really seems to be the case that learning to read strengthens the whole language system. And it kind of makes sense because it gives you a new entry point to the language. So if you remember the triangular lexical representations, you basically just get a new node for each lexical representation where that allows the activity to kind of brush around in a novel way. And so the advances that we have been able to make in the neurobiology of dyslexia are then allowing us to design better interventions for children who are learning to read and who are struggling with reading. And we're also able to track the effect of those interventions neurally, since we now have a good understanding of what the visual word form area is supposed to be doing and what it seems to do in dyslexia. So for example, we now know that even relatively brief training on these grapheme to phoneme correspondences can enhance the visual word form response in little kids like 6. That's a wrap for reading. And next time we'll talk about lexical access. So how do we actually understand words?